So thank you very much for coming to the seminar on arithmetic geometry and quantum field theory and the conference on geometric Langlands. Tonight, it's a great pleasure to introduce Edward Witten from the Institute for Advanced Studies, and he's going to talk about quantization by branes and geometric Langlands.
Thanks, Minhyong, and thanks for the invitation, and also thanks to all of you for coming. So what I'm going to be doing is explaining work with Davide Gaiotto, where we're trying to understand in terms of quantum field theory, a picture that's been developed in recent work by Eddinghaus, Frankel, and Kazhdan, an analytic version of the Langlands correspondence. And there are prior developments which they describe in their references, but I decided the only one I would mention by name is the one I'm closest to understanding because it involves more physics, which is the work of Jörg Teschner. So there are lots of other contributions that should be mentioned, but I'm not the right one to explain them. So I'm going to begin by reviewing the gauge theory approach to geometric Langlands from my work with Anton Kapustin a number of years ago. And that'll be the starting point where we'll see how to make a new twist that will lead us to the current developments in the work of Eddinghaus, Frankel, and Kazhdan. So the starting point for geometric Langlands is a certain four-dimensional gauge theory that has a gauge group G, or it has a Langlands Goddard-Neutz-Olive dual group, G dual. I'll use this symbol for the dual group. And this theory, obviously I'll say a number of things that are very schematic, because if you're not already familiar with this theory, you won't understand in detail what it is from my schematic explanation, but maybe it will set the stage a little bit. So the theory, apart from the choice of a simple E group G, depends on the choice of a real coupling constant and theta angle, which combine to a complex parameter. Actually, I left out the square root of -1 here. So that should be 4 pi I over E squared. So tau is a parameter in the upper half plane. There's an elementary symmetry of shifting tau by 1. But importantly, the theory based on the dual group has an analogous symmetry. Well, the theory based on the dual group on elementary grounds has an analogous parameter, tau dual, also with an elementary symmetry. But importantly, there is something that physicists call electromagnetic duality, which goes back to Montonen and Olive in 1977, which says that theories based on G and G dual are equivalent under this mapping, where tau of the dual group is -1 over tau times 1 over an integer. The integer is 1 for simply laced groups, and otherwise it's 2 or 3. So this paper came out in 1977, and Michael Atiyah immediately, well, he was the one who drew it to my attention. I'd never heard of the Langlands program at all, but he noticed that this conjecture involved a relation between the group and the dual group, and kind of predicted it would somehow be relevant for the Langlands program. Now, this duality that I stated on this slide isn't particularly a statement about geometric Langlands. And people studying this duality are usually studying questions with no obvious relation to geometric Langlands. Unfortunately, to try to give an impression to a general audience of mathematicians of what one usually does with this theory would really take the whole hour, and that would still be very challenging. But trust me that most people working on this duality are miles away from geometric Langlands. It's a much, much more general duality than geometric Langlands. We have to specialize it a lot to get anywhere close to geometric Langlands. To do so, we first consider what's called a topological twist that leads to a family of topological field theories, parametrized by complex parameters psi or psi dual. And if we study the whole family, then first of all, we get electromagnetic duality again, a symmetry between the group and the dual group. We also have these more elementary symmetries. And together, this becomes the duality of what is called quantum geometric Langlands by practitioners of that field. But for today, we're going to consider only the basic geometric Langlands duality between two special values, psi equals 0 for the group G, and psi dual equals infinity for the dual group. I'll call these the A model and the B model because they are closely analogous to the A model and the B model in the context of mirror symmetry. Now, in general, a quantum field theory in dimension D associates a number to a D manifold. The number is called the partition function. a vector space, the space of physical states to a d minus 1 manifold, and a category of boundary conditions to a d minus 2 manifold. That one there should be a 2. So in the present context, we're going to keep fixed a Riemann surface C in which we're doing geometric Langlands. So we're only going to consider 4 manifolds of the product form, sigma times C, where sigma is another 2 manifold. This is part of what I mean when I say we're specializing a lot to get anywhere near geometric Langlands. First, we considered a certain topological twist, which throws away most of the stuff, actually. And then we specialize to this kind of 4 manifold. Anyway, if we keep sigma C fixed and let only sigma vary, then we define a category of boundary conditions that depends on C. In other words, for fixed C, we effectively have a 2-dimensional field theory with sigma arbitrary. And to a point, a 2-dimensional field theory will associate a category of boundary conditions, except here the category will depend on C. Now, it's convenient to draw 2-dimensional pictures in which we only exhibit sigma and not C. So I'll draw some pictures where we completely hide the Riemann surface that we're actually studying when we do geometric Langlands. So sigma will be allowed to be a Riemann surface, a 2-manifold with boundary. Sigma will be an oriented 2-manifold, but it may have a boundary. So first I've drawn a local picture near the boundary. So here's sigma, and here's its boundary, and sigma, the plane is always oriented, so sigma is oriented, and that induces an orientation of the boundary, shown by the arrow. And to formulate quantum field theory on sigma, we need to specify a boundary condition. Now, boundary conditions make well, I told you there was going to be a category for a theory on a 2-manifold, and the objects in this category will be boundary conditions. Boundary conditions are a category as follows. Given 2 boundary conditions B1 and B2, Hom from B1 to B2 is the vector space that quantum field theory assigns to this picture. So, okay, you see. Now my sigma is a strip that has 2 boundaries, B1 and B2, with opposite orientations. Now I could cut across, I could make a horizontal cut of that picture, and the horizontal cut will be a compact 1 manifold. And the compactness is important. To a compact 1 manifold, that's now codimension 1, because this is a 2-dimensional theory. So to a compact 1 manifold, we assign a vector space. And that vector space is Hom from B1 to B2 in the category of boundary conditions. I should warn you, physicists only use this terminology in special problems where it's useful. So you could talk to a large assortment of physicists and they wouldn't tell you that boundary conditions form a category. You'd have to pick people who work on the right kind of question. Now, in category theory, you'd expect that if you said B1 equals B2, then Hom from B1 to B2 should be an algebra. And I've indicated it by this picture here. So the input in this, there aren't arrows. Perhaps I should have drawn arrows to show that the orientations, but the input, think of time going upwards. The input is an element of Hom from B to B, another element of Hom from B to B. The output is an element of Hom from B to B. So Hom from B to B is an algebra. A similar picture with 3 strings joining would show that it's an associative algebra. And moreover, similar pictures where you label the boundaries by different objects, B, B prime, and so on, would show, for example, that Hom from B to B prime is a left module for Hom from B prime to B prime, and so on. All the things you'd expect in category theory. So electric magnetic duality will give an isomorphism between the category curly C associated to the Riemann surface C in the G theory at psi equals 0, and the corresponding dual category associated to the same Riemann surface in the G dual theory at psi equals infinity. In addition, there's a natural mapping between certain natural functors on these 2 categories. The functors come from what physicists call line operators. So in a quantum field theory defined on a manifold M, in general, a line operator is some sort of modification of the definition of the theory along an embedded 1 manifold, which I'll call K. So at both psi equals 0 and infinity, there are natural line operators. At infinity, there are what physicists call Wilson operators. A Wilson operator is the holonomy of a gauge field interpreted as an operator in quantum field theory. And we'll get to special cases at the end of the lecture. And then at psi equals 0, the natural line operators are what physicists call 't Hooft operators, which correspond to the Hecke functors of geometric Langlands. In physics, Wilson and 't Hooft operators are usually used in analyzing questions such as why quarks are confined in atomic nuclei, and other subtleties involving the universality classes of quantum field theories. So in that situation, the most common 4 manifold would be R4, and you'd consider various embedded 1 manifolds K. But for us, our 4 manifold will be the product of 2 Riemann surfaces, and I'll tell you in a moment what K will be. For us, a line operator is a functor from the category of boundary conditions to itself. We can understand that statement from this picture. Well, first I'm drawing a purely 2-dimensional picture. So in the purely 2-dimensional picture, an object is a boundary condition, symbolized by this B for boundary condition. A line operator is T, where T might stand for 't Hooft, which corresponds to a Hecke functor. And then you could see that in topological field theory, the distance between T and B is meaningless. You could bring T up to the boundary, and you could think of the composition of T and B as just defining a new boundary condition in the same theory. So this picture represents the action of T on B. So I've written this in words now. The point in part A of the picture is that a line operator T that runs along a boundary with some boundary condition B makes a new boundary condition TB. The point of the second picture, unfortunately, when I introduced categories, I neglected to introduce the functors. A functor between, let's say, an object B and an object B prime, one way to represent it is a junction between 2 parts of the boundary that are labeled by different boundary conditions. So here, the boundary picture gives a functor from B to B prime and another functor from B prime to B double prime. The picture in B.
Sorry, do you mean functor or morphism?
Morphism, sorry. Thank you, Greg. It's lucky, as you can see, I'm not that familiar with the language I'm trying to use in order to make the lecture understandable. So I'm lucky to have people like Greg on the line who not only know the physics well, but can straighten me out when I stray. So thanks, I appreciate it. So part A explained how T acts on objects of the category, but I wanted to explain how it acts on morphisms. So actually I did give you a picture for a morphism, but another picture of a morphism is that it's a junction between 2 parts of a boundary which are labeled by different boundary conditions. So on the left, I have a morphism from B to B prime, and then another morphism from B prime to B double prime. I claim that T is a functor on the category, which means it acts on objects as in part A, but it also has to act on functors, obeying certain axioms. And the axioms are obvious from this picture here. In other words, however the junctions on the boundary compose, when you don't worry about T, they compose the same way when you introduce T in the picture. So the 2 pictures, if you understand them, explain that line operators are functors on the category of boundary conditions. Now I've been drawing pictures in 2 dimensions, but there are 2 more dimensions not drawn. And although in general, in the physical duality, we could consider a line operator on an arbitrary 1 manifold in 4 dimensions, we're going to specialize to the case that our 1 manifold is actually the product of a point P and C times a 1 manifold in the picture. So as I told you, we specialize a lot to specialize this much more general duality to get geometric Langlands duality. And this is another aspect of the specialization. So the pictures really have 2 more dimensions not drawn, and T depends on the choice of a point in the 2 dimensions that aren't drawn. Now, an important property of Hecke functors is that they commute. Let's say Hecke functors associated with different points P and P prime commute. And if you remember the two extra dimensions, the commutativity is obvious here. So you see, first of all, the picture describes acting on a boundary condition P, B, not labeled, but the boundary without the line operators would be B. Then I take T of P labeled by this line and move it to the boundary. That gives T of P acting on B. Then I take T of P prime and move it up to the boundary. And then I get T of P prime times T of P acting on B. So in general, this is just the composition of 2 functors in a category, and they might not commute. But in this case, the functors depend on additional points in 2 extra dimensions that aren't drawn. And that makes it obvious that we can move the line operators through each other with no singularity, and therefore the Hecke operators commute. So that's the commutativity of Hecke operators from this point of view. It follows from the fact that there really was a topologically invariant construction in 4 dimensions. And although the categorical picture in 2 dimensions wouldn't show why T of P and T of P prime commute, above 2 dimensions, it's obvious. I spelled that out partly because we will have several later examples of the same commutativity.
Sorry, couldn't there be braiding of the T of P and the T of P prime? I mean, the P and prime are moving around.
Correct, that's a good, excellent question. In 1 dimension more, there could be braiding. In other words, there could be, with 1 extra hidden dimension, you'd be able to prove that there are commutativity isomorphisms, but they wouldn't be unique because P could go around P prime either above or below the picture. But there are 2 hidden dimensions. So
Sorry, okay, yeah, got it.
There can be no braiding, but experts on such things would tell you that there is a sort of a hierarchy of higher commutativities. And this tells you how high you can go in the hierarchy with 2 hidden dimensions. So the dual categories C and C dual are equipped with dual families T of P and W of P of functors, parameterized by the choice of a point in C and some more data and commuting at distinct points. So as I've already said, T of P corresponds to the usual Hecke functors, and WP is its dual in the usual geometric Langlands duality, which is often not stated explicitly in mathematical treatments. Since these functors, it's often not stated explicitly because it's too elementary. Since these functors depend on more data, namely a representation of the dual group. You see, on the Wilson side, W is a holonomy operator, and to take holonomy, you need a representation. Or you take the parallel transport in an associated bundle to the G dual bundle G in a representation R. So the Wilson operator depends on a representation of the dual group, and therefore duality says that the Hecke operator does as well. So since there's more than one Hecke operator at a given point, you can consider the composition of Hecke functors at the same point P associated to possibly different representations of the dual group. They commute, but slightly less obviously. But you can naturally compose them, and the duality says that the algebra of compositions of Hecke operators is the same as the corresponding algebra of Wilson operators, which on elementary grounds is the tensor algebra of representations of the dual group. So it's kind of tautology from the way holonomy is defined, that if you take the tensor product of 2 vector bundles, you get the holonomy in the tensor product bundle. That's all this statement is. You can expand the right-hand side into a sum of irreducibles. The duality says that the algebra of compositions of Hecke operators is the same, a statement that mathematically is known as the geometric Satake correspondence. Actually, I could just barrel ahead, but we could also stop for a moment if there are questions.
I have a naive question.
Yes.
How should one think of an eigen boundary condition? So you showed how the Hecke operators act, but if the boundary condition were eigen, it just leaves the, so what would be the eigenvalue basically? That's
Well, first of all, it's a very good question. It's more a question about my work from 15 years ago than the current work. And that's why I haven't prepared to explain it today. The quick answer is that an elementary argument shows, actually, let me postpone answering it till I finish explaining this slide.
Thank you.
I want to introduce a useful language for formulating a simplified version of geometric Langlands duality, and then I'll go back to the question. So I'm going to introduce the moduli space of Higgs bundles on C for gauge group G. So as shown by Hitchin, it's a hyperkähler manifold. So in one complex structure, it parameterizes Higgs bundles, but in another complex structure, which Hitchin called J, I and J are Hitchin's notation, it parameterizes flat bundles over C, where the structure group is the complex group G sub C. then I, j, and k equals ij act as the usual unit quaternions. And in Hitchin's work, there also are the corresponding three Kähler forms, omega I, omega j, and omega k, which are Kähler with respect to I, j, and k. So geometric Langlands duality for many purposes can be understood as a mirror symmetry between the A model of Hitchin's moduli space of G in symplectic structure omega k and the B model of the dual group in complex structure J. This is a particularly simple instance of mirror symmetry, which was first studied by Hausel and Thaddeus a few years before my work in this area. So the question was, what's an eigenbrain? And the answer is on the B model side, an eigenbrain for the Wilson operators. See, an object in the B model is an object in the derived category of coherent sheaves. But an eigenbrain is simply a coherent sheaf supported at a point. And the dual A eigenbrains are therefore the mirror duals of a B brain supported at a point. And according to Strominger, Yao-Zaslow, and Hausel and Thaddeus, those are certain Lagrangian brains supported on a fiber of the Hitchin fibration. And you can actually explain explicitly why they are correspond to eigenbrains for the Hecke operators. But that is a lecture I would have given 15 years ago. It's not the one I planned today.
Thank you.
Any other questions?
Sorry, I think Theo has a question. Theo, would you like to unmute and ask your question?
Well, it was a sort of, it was a basic question about Edward's work from 15 years ago, apparently, but it was just I understand, I think that what you're telling us is sort of the story that I understand of duality has to do with having one quantum field theory and two different Lagrangian descriptions. And I was wondering to what extent that's like what you were doing. You're kind of computing this theory in two different Lagrangian descriptions, and to what extent how much were you looking for things the mathematicians already knew versus finding new dualities? So a specific case being, for instance, these Hecke functors, like recognizing those within the quantum field theory. Should I understand the logic being, you do this computation in this Lagrangian description and you discover that this is the answer, or was there something more to it?
It was very hard to understand what mathematicians were saying. Honestly, mathematicians were using ingredients that were familiar in physics, but it looked like they were scattered at random on the chessboard. In particular, the logic behind the definition of Hecke functor eluded me for years. I was fascinated by it for years and years. Really going back to 1977, when the T had predicted that electric-magnetic duality would be related to the Langlands program. Neither side of that correspondence was familiar to me until he told me they should be related. So I started learning about both. He sent me to London. I wrote a paper with David Olive. A lot of things happened later. Eventually, the physics side became well established. Then there was the work of Bailenson and Drinfeld. But for years, I couldn't make any sense out of Hecke functors. Then one very happy day, and it was a very happy day, I realized that Hecke functor is just an algebraic geometer's way of talking about an 't Hooft operator. But really, to give you a better answer to that question would also be another lecture.
Well, thanks. Okay.
Kinds of things today. I'm sorry, I can't do much better. So,
sorry, actually, I might comment. If we can trouble you sometimes, that other lecture would be very interesting, your way of understanding Hecke functors someday.
Well, I'd be tempted to do it, frankly, by explaining it in the context of my work on Covenant homology rather than geometric Langlands.
Okay, great. Yeah, no, I'll bother you again sometime. Okay.
That lecture has a written version online, but I'll be happy to give it in person, so to speak.
Yeah, great. Thanks.
Now, to say that the geometric Langlands duality is a mirror symmetry between two finite dimensional varieties is oversimplified. It's oversimplified in a way that's extremely, okay. The correct statement is the correct statement is what I said before. This is an oversimplified approximation. But what I'm about to tell you about how this first sentence here is related to the correct statement is extremely simple, yet I know that it's extremely hard for mathematicians to understand the following. There are all kinds of questions for which the two-dimensional picture is inadequate, and anyone who works on geometric Langlands from a standard mathematical point of view will know this well. They describe this by saying that the theory should be formulated on the stack of G bundles, not on a finite dimensional moduli space. There are technical reasons in all possible directions that that's necessary. What does it mean for a physicist? Physicists describe it by saying that the correct formulation is a duality of four-dimensional theories, and the two-dimensional description is an idealization. Now, the connection between the last two sentences, this one of the mathematicians and this one of the physicists, is extremely simple, but yet might be unfamiliar. Atiyah and Bott showed in 1981 that a model of Bun G is the space of all connections on a fixed smooth G bundle over C. So what we really want, which is a two-dimensional theory whose target is Bun G, is better understood as four-dimensional gauge theory. In other words, if I pose to you the problem, invent a quantum field theory that makes sense, which is a two-dimensional quantum field theory whose target is Bun G, but it's supposed to make sense. And as a clue, instead of listening to algebraic geometers about what Bun G is, you should listen to Atiyah and Bott. You might still have trouble doing that. You'd need a small trick, which I won't explain now technically, though it would be easy to explain for physicists. But the answer to that question is the four-dimensional gauge theory. So when mathematicians say that the correct statement is on the stack of G bundles, not on a finite dimensional moduli space of G bundles, that's an entree to an extremely technical world where the way physicists would describe it is by saying that the duality really should be studied as a duality of four-dimensional quantum field theories. 4 is the minimum, you can go higher, but 4 is the sufficient dimension to make completely correct technical statements. Now, I want to use the two-dimensional description of geometric Langlands duality as mirror symmetry between one Higgs bundle moduli space and another to explain why the category that appears on what mathematicians call the automorphic side of the duality, which means this side, is a category of D modules on Bun G. Well, on the automorphic side, we're studying an A model. It's an idealization to call it a two-dimensional A model, but that will orient you. In the A model or Fukaya category of a real symplectic manifold, the most familiar objects are Lagrangian branes supported on a real Lagrangian submanifold L. Those are the objects mostly studied by mathematicians working on the Fukaya category. But Kapustin and Orlov discovered that in general, one can also define quasitropic A branes that are supported on a quasitropic submanifold that's above the middle dimension. So they discovered it as a consequence of mirror symmetry. They discovered that mirror symmetry didn't work without enriching the Fukaya category to include quasitropic A branes. And we're basically doing, well, a technically completely correct statement is in 4 dimensions, but we're basically doing a version of mirror symmetry. So we need quasitropic branes for the same reason they needed them. The construction of quasitropic branes is delicate in general, but the simplest case is the case relevant to geometric Langlands. That's the case that the real symplectic manifold that's being studied is actually a complex symplectic manifold, whose complex structure I'll call it I, and I'll call its holomorphic symplectic structure capital omega, which I'm writing as omega j plus I omega k, where the notation is motivated by the hyperkähler case. One views Y as a real symplectic manifold with symplectic form M omega, and one takes the B field to be real omega. So that's the simplest case that leads to a coisotropic brane of Kapustin and Orlov. And this is the brane Kapustin and I studied, although we described it in a way that differs from this by what's called a B field gauge transformation. So anyway, with this data, you can construct a canonical coisotropic A brane whose support is all of Y. So this is an unfamiliar object in the Fukaya category, but Kapustin and Orlov showed that to make mirror symmetry true, the Fukaya category should be enriched by allowing such objects, of which this is the simplest. And this is also the most important for geometric Langlands. Now, it has the property to slightly oversimplify that Ham from BCC to itself is related to deformation quantization of the algebra of holomorphic functions on Y. Remember, I said that we're assuming here that Y is a complex symplectic manifold that we view as a real symplectic manifold. So since it's a complex symplectic manifold, it has a commutative algebra of holomorphic functions since it's a complex symplectic manifold, we can do deformation quantization. And what makes quasitropic branes fascinating is that, well, at least this is the simplest version of the statement, is that Ham from the canonical quasitropic brane to itself is related to deformation quantization of the algebra of holomorphic functions on Y. So that would go into a direction of a long explanation, but there's a special case that's easier to explain that's sufficient for today. Suppose that Y is the cotangent bundle of some other complex manifold W with the standard complex structure of the standard complex symplectic structure of the cotangent bundle. In that case, you can show that Ham BCC to itself is the sheaf of holomorphic differential operators on W acting on a square root of KW. K is the canonical bundle of W. You consider holomorphic differential operators acting on a square root of K. As algebraic geometers will know, such holomorphic differential operators exist and are independent of a choice of K to the 1/2, whether or not K to the 1/2 exists or is unique. So this is, well, this is practically the simplest statement about the simplest example of a quasitropic A-brane, and it shows how interesting quasitropic A-branes are, and they deserve way more study than they've gotten. Admittedly, in part because they're hard to study. So this is the simplest example to give, and other examples are not so elementary. In the case of geometric Langlands, we take Y to be the moduli space of Higgs bundles on our Riemann surface C. It's birational to the cotangent bundle of the moduli space of holomorphic G bundles. And so A is going to be the sheaf of holomorphic differential operators on the moduli space. That also means that if B is any other brane, then Ham from that brane to BCC is going to be an a module for Ham from BCC to itself. In other words, the category on the automorphic side of the geometric Langlands duality is the category of, roughly speaking, D modules on the moduli space. Except all these statements, I've expressed them in two-dimensional language, but they lift to four-dimensional statements, which algebraic geometers capture by expressing the statements in terms of stacks rather than moduli spaces. So as I said, mathematically, it's important to work with D modules on the stack, not on the finite dimensional moduli spaces. Physically, what that means is that it's important that a version of BCC can be, BCC, remember, is the canonical quasitropic A-brane. It can be defined directly in 4 dimensions, not only in an idealized 2-dimensional description. Kopustin and I had a version of a 4-dimensional description, but Gaiotto and I improved it a few years later. And that enabled us to answer a number of questions that were, whose answers were known mathematically, but had been a little bit obscure from a physical point of view. And one question that was certainly known mathematically, but was not very clear physically, was what's the dual of BCC? In other words, BCC itself is an A-brane, so its geometric Langlands dual is going to be a B-brane. But what B-brane is it? So its dual is going to be a B-brane, in other words, a coherent sheaf or perhaps a complex of coherent sheaves on the moduli space viewed as a moduli space of flat G-dual bundles. Well, as I said, the answer was known mathematically from the work of Beilinson and Drinfeld. The answer is, see, the D module corresponding to BCC itself is the sheaf of differential operators on the moduli space. Its dual, according to Beilinson and Drinfeld, is the structure sheaf of the variety of O pairs, a very special Lagrangian submanifold of the Higgs bundle moduli space. And I won't define it now, but I will at the end of the lecture. So, okay, this is another thing I toiled over for a number of years, because with the description Kopustin and I had of, with the 4-dimensional description we had of BCC, I couldn't see its dual. So one reason this paper was in advance was that the dual became transparent. So now I'm going to summarize the main ideas in the gauge theory geometric Langlands correspondence. First, electric magnetic duality that exchanges the group with the dual group. Second, twisting to make a dual pair of topological field theories. Third, the dual theories have dual sets of line operators that are going to become functors on dual categories. Well, I should, back here when we made the topological field theories, I should have added specializing to a product of two manifolds and consider a category on the first that depends on a choice of the seconds. Then on one side of the duality, there's a distinguished A brane BCC, establishing a map from A branes to D modules. On the other side, one is studying B branes in the moduli space in which it parameterizes flat bundles. And then you have to go on and understand more explicitly what the dual functors are corresponding from 't Hooft and Wilson operators. And there are lots of other fun questions to answer. But for today, we'll have to go on. Although I will stop here for any more questions before we go on.
Sorry, maybe just a terminological question. This deformation quantization that you referred to, is this something that you call in some paper brain quantization?
To
Is
tell
that
the
the
difference between
terminology?
deformation quantization and quantization. So great question, but
Okay.
actually what I'm going to answer next.
Okay, yeah, thanks.
I'm not sure if there are any other questions or if I'll just go on then. So what I've told you so far involves deformation quantization, not quantization. It's extremely important that there's a difference, a huge difference, an ocean of difference between deformation quantization and quantization. Since I want to make the difference completely inescapable, I'm going to give a concrete example of a two-sphere. This is a real two-sphere, so x, y, and z are real variables, and j is a real number, which you might as well consider to be positive because only j squared appears in the equation. And we view the two-sphere as a symplectic manifold with its standard rotation invariant symplectic form, which can be written this way. So what's deformation quantization and what's quantization? In deformation quantization, we start with the commutative algebra of functions on the sphere. And if you're algebraically minded, you might start with complex valued polynomial functions of x, y, and z. And then you want to deform this to a non-commutative algebra. And in general, you specify that the leading non-commutative deformation should agree with the Poisson bracket. So you ask for a family of commutative algebras over a polynomial ring C of H bar, or maybe a formal power series ring. But anyway, you ask whether you can make optimistically over this ring, or you can make a family of associative but not commutative algebras over C of H bar, which at H bar equals 0 degenerate to the commutative algebra functions, this one. And then you want the leading deformation to be the Poisson bracket. That's the problem of deformation quantization. In the present case, you can just write down the answer, which is given by the SU2 Lie algebra. So this algebra answers, together with this relation, answers the problem of deformation quantization in this example. But there's a theory by Fedosov, Kontsevich, and lots of other people giving general answers to that kind of question. Now, j didn't have to be an integer, a half an integer, or anything. In fact, if you're algebraically minded, you would say that j could have been a complex number, which is even true. Then we should have said that x, y, and z are complex variables, and we're doing deformation quantization of the algebra of holomorphic functions on this complex symplectic manifold. And that's relevant because that's actually what I introduced a little while ago. Here, I said that A is, where did I say it? Well, somewhere I said, but I didn't find it in scrolling through. Somewhere I said that in the case of the canonical quasitropic brane, Ham from that brane to itself is deformation quantization of the ring of holomorphic functions. So the same kind of thing I said here, but considering holomorphic functions. But none of that is quantization, and that's extraordinarily important. Quantization means finding a Hilbert space, which roughly is of the appropriate size, but I won't try to explain what that means today, that the algebra acts on. In this particular example, quantization means finding an irreducible representation of the algebra, irreducible unitary representation. Unitary means that x, y, and z are Hermitian operators. An irreducible unitary representation doesn't exist for arbitrary j. If you've studied either quantum mechanics or else the Lie algebra of SL2, you perhaps know that you can only quantize this algebra, this and thus this symplectic manifold, at special values of J at which the Hilbert space exists. Those are the special values that correspond to the angular momenta in the real world of electrons, atoms, and molecules. Deformation quantization is a purely formal construction of an algebra. If you actually want to discuss the things that exist in the real world of quantum mechanics, you're talking about quantization, not deformation quantization. And you need the appropriate algebra, the appropriate Hilbert space that your algebra acts on. It's because of the last step that the subject is called quantization. Quantization means that J, the angular momentum of classical mechanics, doesn't take arbitrary values, it only takes special values where the Hilbert space exists. In deformation quantization, that's just not true. You only quantize the parameters when you actually quantize the theory and construct a Hilbert space. That's why personally, I try to always use the terminology deformation quantization when that's what I mean, although unfortunately it becomes clumsy sometimes. Now, the story as I've told you so far involves deformation quantization and not quantization. But a couple years later, Sergei Gukov and I asked whether the A model in this general setup can describe quantization and not just deformation quantization. And the answer is yes, under certain conditions. Recall that in general, we're discussing a complex symplectic manifold Y viewed as a real symplectic manifold with a symplectic form M omega. Let's discuss Lagrangian A-branes, which means, by definition, A-brane supported on a submanifold L that's Lagrangian for M omega. Now, in many of the examples important in geometric Langlands, L is actually a complex Lagrangian submanifold, which means it's Lagrangian for omega, not just for M omega. But that's a very special condition. Most Lagrangian A-branes don't have that property. And the geometric Langlands correspondence is formulated as a statement about all A-branes, not just the exceptional ones that are Lagrangian for omega. So we could apply the correspondence to branes that are not Lagrangian for omega, only for M omega. So here I've given an example of an important one. One of the questions was about eigenbranes. So eigenbranes on the G-dual side are skyscraper sheaves. On the G side, they are Lagrangian branes supported on a fiber of the Hitchin fibration. A fiber of the Hitchin fibration is a complex symplectic manifold. So this is an example important in geometric Langlands where L is complex symplectic, not just symplectic for M omega. But it's a highly non-generic situation. So Sergei and I decided to look at the opposite case of an A-brane that's Lagrangian for M omega, but it's symplectic rather than Lagrangian for real omega. That's the opposite case from the case of a complex Lagrangian, complex symplectic submanifold. We showed that in this case, HOM from B to BCC is a quantization of L with symplectic structure real omega. That statement only makes sense because L was assumed to be symplectic for real omega. But nevertheless, it was Lagrangian for M omega, so it's an A-brane, and we can look at HOM as an A-brane from B to BCC. And we showed that that vector space is a quantization of L with symplectic structure real omega. That was kind of the main point of our paper. So for example, if Y is an affine variety, then the holomorphic functions on Y, which are deformation quantized to get HOM from BCC to itself, are analytic continuations of certain real analytic functions on L. And those real analytic functions, there are enough of them to be a reasonable quantum deformed algebra of observables. And those are the functions that act on this quantum Hilbert space.
So is there a natural Hilbert space structure here?
Yes, I'm very happy with, well, first of all, the audience is doing excellently because some questions were things I forgot or errors you pointed out, but quite a few questions have involved the next sentence even. So I stated this in too big a generality for there to be a Hilbert space structure, but there's a reasonable condition. Okay, Sergei and I showed that there are interesting examples of this which are not Hilbert spaces. For example, we considered Harish-Chandra modules for SL2, which are not necessarily unitary, but they can be unitary. So non-unitary Harish-Chandra modules were examples of this construction that didn't have an additional condition, and unitary ones are the case that additional condition I'm about to impose is valid. So the case with or without the Hermitian structure is both interesting, but for today, we want the case with the Hermitian structure. So we showed, it wasn't the next sentence, despite what I said, it's the next slide. We showed that Hom from B to BCC is a Hilbert space if you impose a certain natural condition. In general, if B1 and B2 are any branes, there is a non-degenerate bilinear, not Hermitian pairing from Hom B1, B2 to Hom B2, B1. To get a Hermitian inner product, a non-degenerate Hermitian inner product in Hom B1, B2 is therefore the same as finding an antilinear map from Hom B2, B1 to Hom B1, B2. And Gukov and I showed that there is such an antilinear map if there's an anti-holomorphic map tau from Y to itself with M as a component of its fixed point set. So that's the condition that leads to having a Hermitian inner product. I won't explain how we define theta tau, but I will explain why you should expect you need a condition like this. If holomorphic function—
Sorry, what was capital M, capital Latin M? What was it?
Capital M is the support of a Lagrangian A-brane. I hope, oh, I see, I called it L. Oh, okay, right. Okay, I switched from L to M in the middle of this page. So M is the support of a Lagrangian A-brane, which is symplectic for real omega. Then you get something that has all the properties of a quantum vector space, except it may lack a Hermitian pairing. To get a Hermitian pairing, it should be the fixed point set of an antilinear map from Y to itself. And I'll just explain heuristically why you should expect this criterion. If holomorphic functions on Y act on H, and H is a Hilbert space, one will have a notion of which holomorphic functions on Y are Hermitian, which in the classical limit ought to be which functions are real. So you should have a notion of a holomorphic function on Y being real. And that's what you have if M is a component of the fixed point set of an anti-holomorphic involution of Y. It gives on the holomorphic functions a notion of which functions on M are real. A holomorphic function on Y is real if it's real when restricted to M, and those are the ones that become Hermitian operators after quantization. If we don't have a condition like this on M, then we'd have no reasonable notion of what functions should become Hermitian, so we shouldn't expect to have a Hermitian product on the Hilbert on the quantum vector space.
Edward, could I interrupt with?
Yes, please.
I think Dennis, the gate scorer, seems to have a question.
Yes.
Dennis?
Yeah, thank you. I just want to ask, what is B in the geometric Langlands theory? In the D-module language?
Well, in the story of Eddinghaus, Frankel, and Kazan, I'll tell you what it is in a moment. But in geometric Langlands story, there are various examples that are interesting to study. Because the condition I gave, which is that it's, I don't have a good answer to give you. I don't know what examples would be interesting in usual geometric Langlands, but I will in the lecture explain what we do in the case of Eddinghaus, Frankel, and Kazan.
Oh, so there's not a single B, it's just it's many possible Bs. It's not a particular distinguished B that you have in mind, right?
Well, there will be later, but for now it is different ones.
Okay.
So for example, suppose you have the modular space of Higgs bundles. It has an antilinear involution studied by Hitchin with many components of the fixed point set. So it's interesting to study each of them.
Yes.
Okay, so, well, it's interesting to study all the examples that satisfy this condition as well as the ones that aren't really unitary that lead to Harish-Chandra modules. There's a lot here that's much more interesting that hasn't been done, really. But I want to get to geometric Langlands and the rest of it. Well,
yeah, okay. Great. Okay, thank you.
Okay. Okay. So I've gotten through the preliminaries, and now we can try to, unfortunately, I've used most of the hour, but I have a little bit of an excuse that there were some questions. I realize it's only a partial excuse, but to explain the story with Eddinghaus, Frankel, and Kazan, we'll really have to go over the hour. So, well, given tau, the Hermitian product for any pair of tau invariant branes is defined by this formula. So the smooth bracket is the pairing in the A model, which is bilinear, and the angle bracket is a Hermitian pairing. So we get, given tau, we get a Hermitian pairing for any pair of tau invariant branes. It's always non-degenerate, but in this generality, it's not always positive definite. For the more specific case relevant to quantization, the best I can say is that it's positive definite if you're sufficiently close to a classical limit. So now we're going to get closer to Eddinghoff, Frankel, and Kazhdan. In this approach to quantization, if you're given a real symplectic manifold M that you want to quantize, you have to find the complexification of M to a complex symplectic manifold Y with some appropriate properties. And then you can use the A model of Y to quantize M. So you can't always quantize M because a given M might not have a Y. That might be loosely compared to geometric quantization, which is the closest thing there has been to a systematic approach to quantization. In geometric quantization, to quantize M, you have to find what's called a polarization of M, roughly a maximal set of Poisson commuting variables. Then given a polarization, geometric quantization gives a recipe for quantization. So, well, I don't have time today to explain geometric quantization. I've schematically explained quantization by Branes. Either of them needs something, a polarization in one case, a Y in the other case. And either one can give good results if there's a natural polarization or a natural choice of complexification for the problem at hand. Neither one is an all-purpose answer. A limitation of my paper with Gukov is we didn't understand very much about how to compare brane quantization to geometric quantization. Guyotto and I were motivated in the last few months to understand this better as background to understanding the work of Eddinghoff, Frankel, and Kazhdan. And at some level of precision, we've been able to get the best answer you can hope for, sort of, which is that if M can be quantized in both ways, and the data used for one quantization is compatible with the data used for the other quantization in a certain sense stated here, then the two methods of quantization agree. So anyway, under certain conditions, you can compare brane quantization to geometric quantization, but in general, either may apply when the other doesn't. And also, I've oversimplified what's true in the case of a complex polarization, since a detailed statement would have been too long. So all this is by way of preparation to what I actually was the announced topic, which is the work of Eddinghoff, Frankel, and Kazhdan. So they consider a Hilbert space H of L2 functions, or better, half densities, on the moduli space of stable holomorphic G bundles over a curve. They constructed operators on H that are related to the usual constructions of geometric Langlands and found interesting duality theorems and conjectures concerning the action of these operators. I won't state the theorems and conjectures right now. Rather, as we proceed with the physical setup, we'll see what those statements might be. So in geometric quantization, what's the space, Hilbert space of L2 functions on M of G? Well, we understand it in terms of quantization of the cotangent bundle T star of M of G. And T star of M of G is essentially Hitchin's moduli space, the moduli space of Higgs bundles. More exactly, it's birational to M Higgs bundle moduli space. So roughly speaking, they agree outside a set of measure 0, which isn't very important in an L2 theory. But I think the really precise statement is that everything comes from 4 dimensions. This kind of statement is a 2-dimensional simplified explanation. So the Hilbert space of EF and K, Eddinghoff, Frankel, and Kazhdan, is what you get if you take the Higgs bundle moduli space MH of G with real symplectic structure M omega and quantize it via geometric quantization using the fact that it's a cotangent bundle. So on the other hand, we want to study this Hilbert space using duality. But to apply arguments of duality, we can't use geometric quantization. We have to use quantization via Branes. So, well, that's why we more carefully studied the relationship between brane quantization and geometric quantization. We wanted to know that in this situation, brane quantization really does give geometric quantization, which Gukov and I hadn't shown. So, the first step in quantization by Branes is to complexify MH of G, the Higgs bundle moduli space. However, any complex manifold Y viewed as a real manifold has a canonical complexification, namely what I'll call Y hat, which is Y1 times Y2, 2 copies of Y with opposite complex structures I and minus I. Now, Y hat comes with an involution that exchanges the 2 factors. I called it U hat here, but this is meant to be Y hat. y hat has an involution that exchanges the two factors, it's anti-holomorphic because the two factors have opposite complex structures. The fixed point set is the diagonal in y1 times y2. So this is the correct setup. Well, let me articulate it more before saying that. Then, since the complex structures are opposite, we take the holomorphic symplectic form on y hat to be the direct sum of half omega on y1 and half omega bar on y2, where omega bar is the complex conjugate of omega. And this funny box plus symbol means you pull omega back by one projection. You take the two projections from y hat to y1 times y2, pull this back by one projection and this back by the other projection, and then just add them. So that gives a holomorphic symplectic form on y hat. But you can see that the restriction of omega hat to the diagonal y is real omega, which, in other words, the restriction of m of omega hat, there should be hats here. The restriction of m omega hat to the diagonal is 0, and the restriction of real omega hat to the diagonal is one of Hitchin's scalar forms on the Higgs bundle moduli space. So with this choice, the diagonal has the property that it's symplectic for the real part of omega and Lagrangian for the imaginary part of omega, where I'm missing hats. These should have hats. Omega hat, the complex symplectic form of y hat, has the property that when you restrict it to the diagonal, you'll learn that the diagonal is symplectic for real omega and Lagrangian for m omega. So that's the situation in which quantization of y using a Lagrangian brane B supported on y makes sense. Moreover, well, I didn't explain what I meant by holomorphic polarization, but we're in this situation. I told you that there was a certain situation where Gaiotto and I showed that geometric polarization agrees with polarization, geometric quantization agrees with quantization by branes. And luckily, we're in the right situation. So the Hilbert space they study can be studied by brane quantization. But we have to ask, what are the observables in brane quantization? Let's recall Hitchin's integrable system. The Higgs bundle moduli space has a Hitchin fibration, pi from the moduli space to B, where B is Cn for some n. The linear functions on B are Hitchin's commuting Hamiltonians. And classically, the global holomorphic functions on the Higgs bundle moduli space are just the pullback of holomorphic functions on B. So the algebra A0 of holomorphic functions on the Higgs bundle moduli space is the algebra of polynomial functions of the Hitchin Hamiltonians. Well, what are the quantum observables in brane quantization? So by the way, this algebra isn't nearly as rich as it would be if we were studying an affine variety. So that's why eventually one will need Hecke functors to get a sufficiently rich picture. The global holomorphic, we could have studied the sheaf of holomorphic functions, and locally there are a lot of them, but the global holomorphic functions are few. So they're interesting and important, but they're not sufficient to characterize the situation well. So what are the quantum observables in brane quantization? Well, for brane quantization, we define the canonical quasitropic brane, which I'll call BCC hat of y hat, which was a product. It's just a product of canonical quasitropic branes on the two factors. So the algebra that acts on the quantization of y is just a product of two algebras, A and A bar. One is Hom from BCC1 to itself, the other is Hom of BCC2 to itself. They're quantum deformed versions of A0 and A0 bar, where A0 and A0 bar are the holomorphic and anti-holomorphic functions on the Higgs bundle moduli space. But as I told you, the holomorphic functions are just the polynomials in the Hitchin Hamiltonians. Now, for the Higgs bundle moduli space, you can show that the quantum deformed rings are still commutative. I believe that's true to Hitchin for SL2 and to Beilinson and Drinfeld in general. The quantum deformed objects are the commuting differential operators that are the quantization of Hitchin's classical commuting Hamiltonians. So Kapustin and I actually had another explanation of this commutativity. It was similar to the explanation I gave of the fact that Hecke functors at distinct points commute. So from a two-dimensional point of view, it's not obvious why these commuting classical Hamiltonians can be quantized so they still commute. But from a four-dimensional point of view, it is obvious. So quantization means that the commuting Hamiltonians on the classical phase space become differential operators on the base space. Remember here, the phase space is a cotangent bundle. So this is the situation where deformation quantization leads to differential operators. And Hitchin and Bailenson and Drinfeld showed that the Hitchin Hamiltonians are the symbols of a set of commuting differential operators, acting on k to the 1/2, a square root of the canonical bundle. So this commuting algebra A tensor A bar is going to act on the Hilbert space of L2 functions on the moduli space of bundles. Well, first of all, there's no mystery about the fact that it does act on this space, or at least at some level of precision, there's no mystery. It's just the statement that holomorphic and anti-holomorphic differential operators can act on smooth functions. So holomorphic operators trivially commute with anti-holomorphic ones, and the algebras of holomorphic and anti-holomorphic differential operators here are separately commutative. So therefore, A tensor A bar, at least on smooth functions on M of G, trivially acts as a commutative algebra. But what are the joint eigenvalues of Hitchin's Hamiltonians and their complex conjugates? To answer this question, we want to apply duality. Well, to apply duality, you see, we want to apply duality to Ham from B to BCC, where these were both, B and BCC are both branes in a product space. B hat CC is a product brane, and B is a Lagrangian brane supported on the diagonal. So roughly, we need to understand duality applied to both B and BCC, but since BCC is a brane in a product theory, roughly we have to apply duality to each of these branes separately in a single theory, and also apply duality to the diagonal. Well, as I've explained, BCC1 is the brane associated to deformation quantization. So it's the brane, as I explained before, well, this is where I told you that there was a result of Bailenson and Drinfeld that we struggled for a number of years to understand in physics language. And eventually Gayoto and I got that in a paper I mentioned. But as I explained before, the dual, as mathematicians know, and as we eventually understood to our satisfaction, the dual of BCC is a brane supported on the dual is the structure sheaf of the variety of O pairs. An O pair is a flat bundle whose holomorphic structure obeys a certain condition that I'll state in a little while. And likewise, BCC2 is the brane associated to deformation quantization of the ring of anti-holomorphic functions. So its dual is the structure sheaf of what I'll call L O pair bar, the Lagrangian submanifold that parameterizes flat bundles whose anti-holomorphic structure obeys the O pair condition. But what about the brane B that's supported on the diagonal? Well, there's an unfolding trick that gives a trivial answer to this question. You see, I have the product of two theories. So you could think of it, well, each theory could have been defined separately on a two manifold. And except for the brane B, those are two completely different two manifolds. So I've drawn two leaves here.
Over the Rainbow by Judy Garland on Amazon Music.
Okay. Alexa, please be quiet. I'm not sure what I said that got her interested. That was, I don't know if you heard, but Amazon spoke in the background for some reason. So you see, we had a product theory that, so except for one of the two branes, we had a product theory, and at one boundary, we also had a product brane, so there were still two branches. But at the other boundary, the two branches are glued together. And they're simply glued together by a condition that we're on the diagonal, which means that the fields on this sheet and the fields on this sheet agree on the boundary. So we can unfold it and forget about the diagonal. And now we just have a single copy with two different versions of the canonical quasitropic brane at the two ends. So in this unfolded picture, we're studying the theory of a single copy of the Higgs bundle moduli space. And the Hilbert space is not Ham from a doubled brane to a Lagrangian brane, but Ham between two different Quasitropic branes, where I've told you what is BCC, and unfortunately we take, well, in this language I told you what is BCC tilde, but I don't want to translate it to the unfolded language. You just have to believe me that since this language existed and we can unfold, there is an answer. But roughly, there's the conjugate version of BCC, which appears on the other side. So the Hilbert space is Hom from BCC to its conjugate, now in a single copy of MH. And these are both ordinary A branes. So, they're both objects in possibly a completion of what mathematicians do, but anyway, they're both objects in a single copy of the theory. So to dualize the Hilbert space, all we have to do is dualize these factors. But as I told you, the duals of those factors are the structure sheaves of the variety of holomorphic and anti-holomorphic O pairs. In other words, the varieties in the Higgs bundle moduli space that parameterize flat G-dual bundles over the Riemann surface, whose holomorphic and anti-holomorphic structures, respectively, are O pairs. So the algebra A that acted on this factor becomes Hom from the variety of O pairs to itself, and the conjugate one becomes Hom from the variety of anti-holomorphic O pairs to itself. So here are the two dual pictures. Before duality, the Hilbert space is Hom from a quasitropic brane to its cousin, which is kind of the reflected or unfolded version of itself. And the dual picture, we have two Lagrangian branes, one supported on the structure sheaf of the variety of flat bundles, which are O pairs from a holomorphic point of view, the other the ones that are O pairs from an anti-holomorphic point of view. So the spectrum of A tensor A bar, well, the Hilbert space at least, is the same as Hom from anti-holomorphic O pairs to holomorphic O pairs. Now these are both Lagrangian branes, so this Hom space is just an intersection or Hom space in a version of Floer cohomology. I want to elaborate a little because I think people might be confused by the claim that both holomorphic and anti-holomorphic O pairs correspond to complex Lagrangian submanifolds in the same complex structure. So the G-dual description is by a B model of the Higgs bundle moduli space in the complex structure in which this moduli space parameterizes flat bundles over C with complex structure group. So the complex structure just comes from the fact that the complex Lie group has a complex structure. So for example, traces of holonomies are holomorphic functions in this complex structure. A flat bundle has both a holomorphic structure and an anti-holomorphic structure, both of which vary holomorphically. Well, how could you make them holomorphically? For instance, you could change the complex structure of C. But anyway, there's a holomorphic map. Well, there are two holomorphic maps from the Higgs bundle moduli space to well, you see, you could take C. When you define flat bundles over C, there's no complex structure on C. So you could take either of two complex structures on C, namely the one you think you had in mind, or the opposite complex structure. Then you could define bun-G of C and also bun-G of C bar. From the point of view of the complex structure in which Higgs bundle moduli space parameterizes flat bundles, these two are equally good. So there are two morphisms, one from here to here and one from one to here. And the variety of O pairs and the variety of anti-holomorphic O pairs are simply the pullbacks of a point in one or the other times the other one. So if you take a flat bundle and give either a condition on its holomorphic structure or a condition on its anti-holomorphic structure, those are both holomorphic conditions in the relevant complex structure on the moduli space of flat bundles. Now I'm going to give you the definition of an O pair because we'll need it later. I'll state it only for SL2. There's up to isomorphism, a unique non-trivial extension of k to the minus half by k to the half, where k is a square root of the canonical bundle of C, the two manifold. You pick once and for all one. They're all unique up to isomorphism, but pick one. An O pair is a flat bundle that holomorphically is isomorphic to this one. Likewise, there's an anti-holomorphic extension, also unique up to isomorphism if you ask it to be non-split. And a flat bundle is an anti-holomorphic or pair anti-holomorphically if its anti-holomorphic structure is isomorphic to this one. Now, by the method I explained before using an anti-holomorphic involution tau, hum from B tilde to B carries a Hermitian inner product, which we expect to be positive as it corresponds to the quantization of a cotangent bundle. The dual L up bar to L up likewise corresponds to non-degenerate inner product, which is defined similarly using an anti-holomorphic involution on the dual side. On the dual side, the positivity isn't so obvious. On the what mathematicians call the automorphic side, it's more obvious because we're quantizing a cotangent bundle. The non-degenerate inner product can be defined for any B branes that are exchanged by this anti-holomorphic involution. But for generic B branes, it's not positive definite. Conditions that make it positive definite, well, they didn't exactly use this language, but translated to this language, some conditions of EF and K were Edgar Franklin Kajan formulated conditions and showed that these conditions are satisfied for GL1 by direct computation and for SL2 by a theorem of faultings. Conditions they formulated in the language I'm using now show that the Hermitian form one from L up bar on Hom, on this Hom space, is positive definite. You see, consider a point. Okay, the Floor cohomology has a basis corresponding to classical intersections of the two varieties. So such an intersection corresponds to a flat bundle E that's an O pair both holomorphically and anti-holomorphically. The anti-holomorphic involution tau dual will map E to its complex conjugate flat bundle E bar, which will also be an O pair both holomorphically and anti-holomorphically. If E is not isomorphic to E bar, then the 2 points X and X bar that correspond to these flat bundles are both null vectors for the Hermitian form, which will therefore not be positive definite. So positivity of the Hermitian form requires that if you have a flat bundle that's an O pair both holomorphically and anti-holomorphically, then it's also real, as conjectured by EFK and proved in some cases. Thus, the claim is that flat G bundles that are GC bundles that are pairs both holomorphically and anti-holomorphically are actually real. That is, their structure group reduces to a real form of G. I'd like to improve the argument based on duality to show that it's always the split real form, but I'm afraid I don't know how to do that at the moment. Now, so even if the intersection points are all real in that sense, the Hom space is only positive definite if the intersection points are always transverse. So the duality predicts that the intersection points are real and also transverse.
Edward, excuse me, may I say about the previous slide quickly?
Sure.
So it's
so if you have points with parabolic structure, like at least one,
Yes.
then it actually follows that this is split, because the monodromy at this point for the connection will have residue, which is a real principal element, principal nilpotent element.
Oh, okay, that's an interesting point. That's even
So the form is inner according to your argument, but if you have one parabolic point, it is clear that it is split. If there is no, if it is, you don't have parabolic points, we also are in the same position as you. We don't know how to prove that it is split.
okay.
And
Well,
maybe it is not.
Well, I feel it's going to turn out to be split, but I don't know for sure. But
Yeah,
anyway,
we too. We have the same intuition, but cannot prove, other than in the case of parabolic points.
but I have one bit of good news, which is that the statement you made about the parabolic point is one that I actually can understand. Yeah. So there was a risk you'd give an argument I wouldn't have understood. So positive, so the okay. Positivity of the Hilbert space inner product, as I said here, says that the intersections are always transverse as well as real, which is also part of the story of EFK. So bundles that are an pair both holomorphically and anti-holomorphically are what EF and K call real O pairs. So assuming the duality is true and the Hermitian form is positive definite, the joint spectrum of A and A bar corresponds to real O pairs. But I want to explain what that means more explicitly in case it isn't clear to everyone. So according to Bailenson and Drinfeld, an element of the algebra A of quantized Hitchin Hamiltonians, I'll call the element X. It has two interpretations. One is it's a holomorphic differential operator on Bun-G, and secondly, it corresponds to a holomorphic function f sub x on the variety of O pairs. Similarly, an element X prime of the anti-holomorphic algebra is an anti-holomorphic differential operator on Bun-G and corresponds to a holomorphic function on the variety of anti-holomorphic O pairs. So an intersection point of P of the variety of holomorphic O pairs with the variety of anti-holomorphic O pairs determines a pair of eigenvalues of the differential operators that correspond to X and X prime, namely the function fx evaluated at P and the function fx prime evaluated at P. So that's the concrete statement about the joint eigenvalues of Hitchin's Hamiltonians that follows from the duality picture. And of course, it's part of the story of EF and K. Now, Edinger, Frankel, and Kazan also introduced Hecke operators as operators on the Hilbert space H that arises when we quantize the Higgs bundle moduli space as a real symplectic manifold. I've got to apologize for being way over time, but I think this part of the story is so fascinating that I really want to explain it. So if the chair doesn't ask me to stop, I'm going to continue.
Oh, no, that's okay.
Okay, thank you. I've already explained that line operators of the four-dimensional gauge theory can be used to define functors on the category of branes, which here means the category of boundary conditions. Moreover, 't Hooft and Wilson line operators correspond to dual pairs of functors on the A and B model categories. And the same line operators represent, okay, now what I want to now explain is a result due to EF and K that the same line operators represent operators on the quantum Hilbert space. I'll explain it more in a physicist's language, however. I've tried to explain it with the following picture. So in part A is I had part of this picture at the beginning. So B is here we've got a two manifold with boundary, and T represents a line operator. I've used T for a 't Hooft or Hecke. So we're thinking of a Hecke functor, moving it up to the boundary with the Hecke functor on B. But when I drew this picture before, I only had a one-sided picture. Now that we've got a two-sided picture, I'd like to remark that we could move T over to the other side and let it act on T prime. So that gives a duality that a line operator T acting on in Ham from B prime to B, acting on B with a functor T, will be equivalent to acting on B prime with the dual functor T prime. And the dual functor T prime is what you get by moving this vertical line to the right instead of the left. And then you could exchange left and right by rotating the picture by an angle pi, which preserves its orientation. It's important to rotate it, not reflect it, because the pictures have orientations. And well, I'm sure what I've just explained is described algebraically as a duality between a Hecke functor for a representation and a functor for the dual representation. Now, in part B, I've taken the same, remember I told you that everything in geometric Langlands is an incredible specialization of the general physical picture. So here we specialize to the case that our line operator was parallel to the boundary at a fixed point in C. Now we'll consider a different specialization where the same line operator is perpendicular to the boundary, but at the same point in C. C is the Riemann surface we're studying. So now I have a horizontal line operator. I postpone for a moment explaining what's happening when the line operator meets the boundary. Let's suppose that question has an answer. Now, this picture, read from bottom to top, represents an element of Ham from B prime to B. In other words, an element of the quantum Hilbert space. In physics language, it propagates forward in time, but nothing happens because this is a topological field theory, but then it jumps when you cross T. And up here, you'll have a different vector in the same Hilbert space also propagating. So in this picture, T has become a Hilbert space operator, acting on the Hilbert space that we get by Branes quantization using the Branes B and B prime. However, I have to explain what is meant by the corners. Well, actually, before I get to that, let me give the text here. So A was the picture I gave at the beginning of the lecture, except now I ended the picture with the second brane on the right. So it shows the line operator T as a functor in the category of branes. And since we could move it to left or right, we have duality. In B, the same line operator, assuming we know what is happening at the corners, is used to make an operator from H to H, where H is Hom from B prime to B for some branes B and B prime. But we need to know what the corners are. And the purpose of C is to explain what a corner is in algebraic language. Not necessarily the language I would use lecturing for physicists, but the picture C will make it clear, perhaps to, if you're algebraically minded, what's meant by a corner. A corner is the data we need to map B, to map the boundary condition corresponding to the brane B to a new boundary condition corresponding to the brane B parallel to the line operator T. So the point of C is to explain that the corner represents an element of Hom from B to TB. And then there's a, maybe I should have had another picture for the dual side over here. But similarly, this corner is another, well, I've said at the bottom what the answer is. The upshot of this picture and the dual one I didn't draw is that to define the operator in B, I called it A, but in this picture, to get the picture in B into an operator, you need junctions, alpha in Hom from B to TB, and beta in Hom from TB prime to B prime. Now, the argument that showed commutativity of the Hecke functors corresponding to different points P and P prime and possibly different representations of the dual group goes over immediately to show that the operators, just like the Hecke functors, the Hecke operators commute. Because they live at different points in C, they can be moved up and down without singularity. So here I've drawn a picture with two horizontal 't Hooft operators. And in a purely two-dimensional picture, they might not commute. In general, operators in quantum mechanics don't commute. But because these operators live at different points in C, and because there's really some topological invariance in 4 dimensions, they can be moved up and down past each other without singularity. Moreover, as in the discussion of line operators as functors, we can set P equals P prime, and then the algebra of Hecke operators at the same point is again the corresponding algebra of Hecke functors. So it's governed again by the classical tensor product of representations.
Excuse me, but I have a question. So in our situation, somehow it happens that product of the Hecke operators is just stupid. It's just adding highest weights, not the Clebsch-Gordon. So
that's a good point. Let me suggest an answer to that at the end. In other words, yeah, okay, sorry, right. So, no, I think that's because of the following. If you have an O pair, yeah, okay. I think it's related to an algebraic fact. Okay, yeah, you're right, sorry. That happened because of the choice of corners, I think. So there's a particularly simple choice of corner that leads to the answer you said. So, you see, there was something, even in the language I used here, there was something wrong with where I said it. If you try to compose these two, in bulk, you'll compose the two operators, and they'll have a geometric Satake decomposition. But you also have to compose the functors you used. So as I said back here, the corner is a functor from B to TB, and then the next one will be a functor from TB to T prime TB. So you have to consider the composition of the two functors. I haven't thought it carefully, but I'm pretty sure what will happen is that for the particular, I keep saying functor, but I mean morphism. I hope it was clear. The junctions were morphisms, right? You're seeing how little I know of this language, which I'm trying to use just to be understandable today. There are at least one and possibly more physicists on the line who know the language much better than I do. I hope I didn't cause too much confusion in my description here. This picture showed that the data we have at a corner is a morphism from B to TB. And I didn't discuss carefully the other corner, but it's also a morphism. Now, when we take the composition here, we take the composition of the Hecke functors in bulk, but we have to, in other words, let me use physics language. We have to compose the 't Hooft operators in bulk, and the decomposition will involve the geometric Satake correspondence. But we also have to compose the corners that we use, in other words, the particular morphisms that we use to define what's happening at these corners. And I haven't looked at it properly, but I expect what will happen is that for the simplest defined corners, which are the ones you've implicitly used, and the ones I'll introduce in a little while, the composition projects out the lower terms in the Satake correspondence. I'm pretty sure you could use other corners, and we could even speculate at the end about how to do it. That would enable us to see other terms in the Satake correspondence if we want to do that.
Mm-hmm. Okay, thank
I
you.
don't be mathematically interesting. I'm just claiming it's something, as physicists, we could do it. Whether mathematicians will think it's an interesting generalization, I don't know. So what I said was here was oversimplified because I ignored the corners, even though they're important, and I'd explained them on the previous page.
Mm-hmm.
Now, the Hecke functors commute with each other on the Hitchin Hamiltonians for the usual reason. In a purely two-dimensional picture, it looks like there could be a problem, but in 4 dimensions, it's obvious there's no problem. Now, finally, what we can ask, what are the predictions of the duality for the eigenvalues of the Hecke operators? To answer this, we start on the dual side, where it's always easier to calculate. So we're going to consider, on the dual side, the Hilbert space is replaced by this simple Hom space, which has a basis corresponding to the classical intersection points. And we're going to consider a Wilson operator acting on this Hom space. We'll consider its eigenvalues, and then duality will predict that the eigenvalues of the Hecke operator will be the same. And this the basis we'll use of intersections is the same as the basis of the quantized Hitchin Hamiltonians. It's the basis we used before. Also, we'll find out what kind of data we need for the corners that make the Wilson operator into an operator. Sorry, Wilson operator is physics language, but to make it into an operator on the Hilbert space, we need those morphisms at the corners. And again, duality predicts that the same data will be needed to define the Hecke operations as operators. So if we're given, I need to back up a little bit and just explain a general story about gauge theory. So we're given a bundle over a 4 manifold. I'll call the bundle E. It has a structure group G dual, and we're given a representation R of G dual. We can make the associated bundle E sub R, which mathematicians like to write this way, which also comes with a connection. Now, the Wilson operator in general is defined for any path in sigma times C. So if there's any path in sigma times C, we do parallel transport of the connection ER along the path, and that gives the Wilson operator. For the present application, we pick a point in C and 2 points A and B on the left and right boundaries, which I'll take, well, okay. And we pick a path in sigma times P from A times P to B times P. So I've drawn that. The point P is in C, which isn't drawn, but so A times P and B times B are drawn as if they're just points on the left and right boundaries. Then I've connected them with a path that goes from left to right. That's going to be the support of the Wilson operator. Then the Wilson operator, then in gauge theory, we have a connection on this bundle, and it gives us parallel transport along this path, which will go from a fiber here, a fiber at that point, at this point, to a fiber at this point. So if E sub R was this associated bundle, if E sub R, comma A times P or comma B times P are the fibers of E sub R at A times P or B times P, then parallel transport defines for each connection a linear transformation WR of P from one fiber to the other, or equivalently an element of Hom from one fiber to the dual of the other fiber. I'd like to, so R prime is the dual representation to R, and therefore ER prime is the dual bundle to ER. I'd like to state it more symmetrically. by introducing that duality. So now I have W as the Hom from a tensor product of two vector spaces to C. Now, a quantum operator is going to come from something that's a complex valued function of connections. We don't have that yet. We have for each connection a Hom from a vector space to C. To get an operator, we need to supply elements V and W of the two vector spaces. And then WRP applied to V tensor W will give us an element of C. That'll be a function of connections, assuming V and W are picked independent of the connection. And its quantization will be an operator. An easy operator to evaluate and diagonalize in this case, as you'll see. In general, we'd have trouble. If we were trying to decide whether quarks are confined, we'd have trouble, but here we will not. To avoid unnecessary details, I'll state the following for the case that the dual group is SL2, and R is the two-dimensional representation, which therefore is the same as R prime. But there's a straightforward generalization for any group and representation. So in this picture, the boundary condition on the right boundary is that the G-dual bundle E restricted to the right boundary, that's this boundary, is an anti-holomorphic O-pair. And remember, that means there's a non-split exact sequence where K bar to the 1/2 is the square root of the anti-canonical bundle of C bar. And so we pick a bundle V in this anti-canonical bundle. So J bar is the embedding of K bar to the 1/2 in iso bar. And that gives a vector J bar V in the fiber of iso bar at A times P. Similarly, on the left boundary, we have an embedding J of K to the 1/2 in the fiber. So we pick a W in the square root of the canonical bundle, the fiber at P rather of that. And that gives us a vector J of W in the fiber here. So in other words, the corners that we need correspond to vectors V and W in K to the 1/2 and K bar to the 1/2, where K to the 1/2 is a square root of the canonical bundle of C. Once they're picked, the quantum operator we study is the holonomy from the left to the right, evaluated in this pair of vectors J of W and J bar of V. And that's the complex valued function of connections that we will interpret as a quantum operator. Now, that step is trivial, although it's not quite as trivial as I say in these slides. Edward Frankel gave a lecture on this work 2 hours ago, which made me realize a minor error that I'll correct at the end. But roughly speaking, in the B model, we can actually assume that the connection is pulled back from C. That's because our classical intersection point is irreducible. And using the localization arguments of the four-dimensional version of the B model, you can show that this parallel transport commutes with it and gives an isomorphism between this bundle and this one. So roughly speaking, it shows that the connection is pulled back from C. And in that case, W hat of R of P is just the natural dual pairing on these two dual vector spaces. And therefore, its value at a given real O pair is just the dual pairing between J of W and J bar of V. Now, it's convenient to write the formula this way in terms of V and W, but it only depends on the tensor product V tensor W in K to the 1/2 tensor K bar to the 1/2. And that is sort of not actually a vector bundle, a line bundle with positive real numbers as structure group. So as observed by E, F, and K, there's no dependence on a choice of spin structure. So the spin structure was convenient, but the answer doesn't depend on it. So the duality predicts that on the dual side, the definition of the 't Hooft operator as an operator requires corners, V and W, in these two vector spaces. That's true as was shown by E, F, and K using an algebra geometric formula. And then the duality predicts that the eigenvalues of the resulting operator are what they were on the G-dual side. Namely, they are this pairing between J of W and J bar of V for all the possible real O pairs. However, Edward Frankel's lecture made me realize an oversight. Because SL2 has a non-trivial center, plus or minus 1, the parallel transport from left to right is uniquely determined only up to sign. And therefore the eigenvalues are what I said, up to sign, with both signs occurring. And as he also explained, that's inevitable because on the dual group of SL2 is SO3, the Hecke functor exchanges the two components of the SO3 moduli space. So it's purely off diagonal, and therefore its eigenvectors have to come in pairs with equal and opposite in sign. So that's what I have to offer for today. Although I'm tempted to make one remark in answer to Pavel's question, but this is not something I've thought through deeply. But when we got here, see, if the group hadn't been SL2, this structure would have been more complicated. And as Edward Frankel mentioned in his lecture, a certain power of k bar to the 1/2 would always be embedded in E sub r, but there also are embeddings of other lower powers. So we could have made versions of this construction with other choices of j bar, not just the highest power. And dually, that would have given us other corners. And I don't know how interesting or important it is, but I would guess that we'd see, in that case, the lower terms in the Satake correspondence might not get projected out. But anyway, here I'll stop for any other questions.
Thank you very much. Let's all thank Edward for a wonderful talk first. There have been quite a few questions already. Are there some other questions?
Yeah, we have time for one more.
Yeah, of course.
I have a question. So in the pictures in the end of the talk, where are the electric eigenbrains? If I remember right, the brain of opers itself is not a eigenbrain, right? So how did we conclude
we didn't discuss electric eigenbrains today. So electric and magnetic eigenbrains, we consider line operators as functors on the category of brains. They map B to TB. Then you can ask, first of all, the definition is that if TB is the same as B tensored with a fixed vector space, then in the language of Valentin and Drinfeld, B is an eigenbrain, which I would call an electric and magnetic eigenbrain. So the story of 15 years ago involved explaining what kind of brains are eigenbrains for 't Hooft and Wilson operators. I didn't really explain that today, except a little bit in answer to one question, that the electric eigenbrains correspond to points. Sorry, the structure sheaf of a point on the Higgs bundle moduli space is an electric eigenbrain, and therefore its dual is a magnetic eigenbrain. But that required an explanation I didn't really give today. Today, we were more interested not in T as a functor on the category of brains, but on T as an operator on a Hilbert space, where we have to use these lossy corners at the left and right, which I explained a little bit in this picture. So since that is really a different interpretation, we weren't interested in eigenbrains today. We were interested in eigenvectors. So in today's lecture, T did not really have eigenbrains. It had simply eigenvectors, and the eigenvectors corresponded to these real O pairs. Okay.
So, but is there a connection between the analytical story and the categorical story, in the sense that if I have a eigenobject in the categorical story, I can identify some corresponding function with some corresponding eigenvalue in the analytical story?
Well, I don't want to answer yes or no to that question. I've told you what I understand about what the analytical story is. So in my perspective, the functorials, what's called the categorical story is that you study the A model of one copy of Y and its dualities. The analytical story is the A model of two copies of Y, or better, one copy of Y and one copy with the opposite complex structure or opposite symplectic structure. So that's the relation between the two, and you can do all kinds of things with it.
Okay, thanks.
Yeah. So I also wanted to ask. So in this study of Hecke operators, so we basically were trying to do the same things, and the one of the more difficult points, maybe analytic points, was the following. So you find okay, so you take all the real authors. So real author gives you a single valued joint eigenfunction of the quantum Hitchin system and the complex conjugate. And then, so the question number one, why is that in L2 always? So is there any physics explanation why that has to be in L2?
Well, on the dual side, it was obviously in L2 because
which means that why is the square absolute value of this function integrable? Why is it normalizable, this function?
Well, because it arises, roughly speaking, it arises by quantizing the points. On the dual side, because we simply had a compact set of intersections, it was obviously normalizable. That's one answer. I believe.
Right, but because this kind of space, this Hitchin system has complicated singularities on this divisor of very stable bundles, and it's not so clear why the powers in the power growth near the boundary of this function is not big enough so that it is.
No, I understand the question perfectly, and I had two possible options in answering you, but one was easier than the other, so I gave that one. I really want to explain that answer first. Remember, the L2 functions on the moduli space of bundles are a Hilbert space, but I claim that the duality respects the Hilbert space structure, and that Hilbert space has an L2 basis corresponding to the classical intersections.
Mm-hmm. I'm just trying to think what kind of mathematical argument you could give for it without, which would not require studying these singularities, but some from general principles.
Argument saying that it can all be defined in four-dimensional gauge theory. So
without four-dimensional gauge theory, it is not clear why this function is in it.
It depends on what you want to assume is known, actually. So I thought, I've been thinking a little bit, okay. If you want to give an answer that's close to classical formulas, then I think you need to start with the four-dimensional gauge theory. I think that a completely correct statement in 2 dimensions would involve quantum phenomena that are hard to explain classically. I think the simple picture definitely comes from 4 dimensions. So apart from using the duality, my other strategy to answer you, okay.
The problem is that we do not know how to do 4 dimensions mathematically. So
physicists have the advantage of not having to prove rigorous theorems. That makes it easier to understand a lot of things, which are actually true, but which you aren't understanding at a mathematically precise level. I possibly haven't thought carefully enough, but I think there will be an argument based on 4 dimensions, but there's definitely an argument based on the duality. Mm-hmm. The duality doesn't merely say that an intersection point corresponds to a 1-dimensional space, subspace of the Hilbert space. It's trying to give you a vector in that space. Mm-hmm. Because the 4 cohomology has an integer basis.
Mm-hmm. I see. And another non-trivial question is about basically self-adjoint extension. So we deal with it by using Hecke operators, and if you can show that they are compact, then you get that for free. But otherwise, you would have a question. For example, why if these eigenvectors are in L2, why they are a basis? Why they are complete?
Yes, right.
And so, is it clear from the physics that they are complete?
Well, I'm very uncomfortable in answering a question like this from a mathematician, because if I'm extremely aware that a physicist's concept of the answer to such a question is different from a mathematician's. So I don't like to make casual claims when I don't have to.
Well, but self-adjoint extension is a basically physical notion. It's a
right. The way one would
boundary conditions for the differential operator. So if you just make them act on smooth functions, this is not essentially self-adjoint. So
okay, let me say something that's a little bit intermediate between your point of view and mine. So in your story, you initially define the functions. Sorry, I wish I understood exactly what you define for all bundles whose stabilizer is the center of the group rather than being bigger.
Well, it's basically for GLN, it is just stable. For SLN, it is the same as just stable bundles.
Well, okay. What a physicist would, let me tell you what a physicist would worry about. And then we'll get a little bit closer to understanding how we try to answer the question. So why is it that the two-dimensional description is an idealization? The main reason, or at least one of the main reasons, is that the finite dimensional moduli space has singularities. The singularities are associated to bundles whose stabilizer is bigger than the center of the group. If the stabilizer is still a finite group, that's a very mild singularity, which is definitely not going to cause a trouble. But in the case that the stabilizer is a Lie group of positive dimension, that's the type of singularity that can cause difficulty. And what a four-dimensional gauge theorist would say is that then there's a Coulomb branch of the gauge theory, which you should worry about. Coulomb and Higgs branch, sorry. I didn't plan this carefully, so I didn't think it through carefully. And so the way I'd address your question as a physicist, yes, it's risky because, see, the classical Hamiltonians of Hitchin that are being quantized are unbounded functions classically. And therefore, you should worry about whether they're sensibly behaved quantum mechanically. And what you'd want to show as a physicist is that the Higgs and Coulomb branches, which appear at a singularity, aren't important in this problem. So that's I think mathematically it's hard to see those branches, but you do study the behavior of the wave functions near those singularities.
Mm-hmm. But actually, quantum Hitchin system has singularities on some divisor of very stable, non-very stable bundles. And these non-very stable bundles are still stable. They still have stabilizer just the center of the group. They're just somewhat less stable than the most stable ones, which are generic ones. But they're still quite stable. This is a smooth point. But the equation has a singularity, not the variety.
Yes, I know, but I think it's going to be obvious that nothing bad happens there. The place that, as a physicist, you'd worry about will be the singularities of the variety.
But functions will not be, they will not be C infinity near this point. So is it clear that they're not going to grow too much? I mean, it's true that, for example, for 5 parabolic points on P1, they actually continuous, although they are not differentiable. But this is not obvious. So I'm wondering whether to you it is obvious that they are going to be sufficiently well behaved.
It's obvious intuitively, but I haven't tried to make a careful argument even at a physical level of precision. That's what I'd say.
Mm-hmm.
But it's embarrassing to give that kind of answer to an audience of mathematicians, unfortunately. But okay. As a physicist, I would try to do better with this, and after doing so, I still wouldn't have an answer that would satisfy a mathematician, obviously.
Could I ask a much more superficial question? I'm just displaying my superficial understanding, but I just wanted to check if that was correct anyways. So if I understand correctly, so EFK are developing this analytic theory of automorphic functions for complex curves by doing spectral theory on this L2 of 1G.
Yes.
Right. So do I understand correctly that the main thing that you're doing with Davide is interpreting this L2 of 1G as a brane quantization? And this is what allows you to view this from the point of view of duality?
Yes, that's correct. Once we interpret that Hilbert space as coming from brane quantization, that we can apply the same dualities as before and all the same ingredients as before. You look at them differently and you make different statements. But it's in the same world because it involves different questions in detail using the same ingredients.
Right. So even some of the answers you were giving to Pavel just now, I didn't quite understanding them, but you were saying that they can be explained in terms of the usual dualities then.
Well, I'm not sure which statement you're asking.
Yeah, no, I'm not sure myself. I'm just checking out vague.
He asked about the L2 structure, the normalizability of the Hecke eigenfunctions.
Right.
Well, I'd say that the questions that are asked here are significantly different from the traditional ones. The surprise is that there's a rather different story. That is addressed by a framework for it is provided by many of the same ingredients used in a different fashion. In answer to one of Pavel's questions, I pointed out that on the dual side, one had an orthonormal basis of the Hilbert space corresponding to the classical intersections.
I see. Okay. Sorry. Thank you. I think are there any more questions? I saw some raised hands.
Yeah, maybe I'll ask something. So is there a relationship between the Hilbert space of the complex Chern-Simons theory and this Hilbert space of all two functions on moduli bundles?
Well, in a special case, they are actually the same Hilbert space, right? Okay, what the question is about is that you could study, another thing you could do with the complex Lie group, viewed as a real Lie group. It has a Chern-Simons form, and then you could make a three-dimensional topological field theory where you quantize it. I actually worked on it a long time ago, did some things and wasn't able to do a lot of other things I wanted to do. But the Hilbert space you get that way. One thing I did manage to do was to get a description of the Hilbert space. So yes, I think it is the same Hilbert space. You get the Hilbert space of L2 functions on the moduli space of stable bundles, possibly twisted by the kth power of a line bundle. But k was 0 for today's lecture.
Oh, I see. So you do have a k non-zero version of this story just now?
Well, it depends what you mean by having. Davide knows more of it than I do.
I see. Yeah.
And the statements have a different flavor. They don't really have the same flavor anymore. And more is clear for k equals 1 or minus 1 than for generic values of k. So,
what is k?
Instead of studying half density, so over the moduli space of stable bundles on a curve, there's a natural holomorphic line bundle called the determinant line bundle in the case of GLN.
Oh, you mean non-critical level? Yeah.
Yes, except here it's going to be important to take an integer because we need an actual line bundle over the moduli space. We can discuss differential operators acting on L to any power, but if we want to make a Hilbert space, we have to take an integer power of L. And
no, but you take absolute value of this line bundle, so it doesn't matter whether it's integer.
Well,
I mean, you can have.
You can, but it's not, at least for the theory I had in mind, it's not the right thing to do. There's a natural theory, which I even ran into 30 years ago in a completely unrelated context, which the questioner, I think, was asking about. There's a natural theory where what you get is the L2 Hilbert space of half densities on the finite dimensional moduli space with values in an integer power of the holomorphic line bundle L. In that definition, it's not important that L is holomorphic. It's a smooth line bundle, but anyway. Oh, sorry, it is important. Well, in defining the Hilbert space, it's not important that it's a holomorphic line bundle, but in the way it appeared in the story, it was. Well, I might have put too much into the questioner's question, but part of the question I thought might have been whether the story for non-zero integer has an analog here, or shows up here.
Well, maybe I'll just explain the reason for why I was a bit surprised, because as you say, for general K, these you do get these Hilbert spaces associated to Chern-Simons theory with various levels. And you seem to be saying that there's something like a space of automorphic functions living inside these Hilbert spaces.
Well, I'm really not qualified to use that language.
No,
what I can say is that you can set up an A model similar to the one in this lecture, but a little bit different.
I see.
Which would give you a framework to study that Hilbert space. And you can make duality statements. But it's a little bit like quantum geometric Langlands. In classical geometric Langlands, you have D modules on one side and coherent sheaves on the other side. In quantum geometric Langlands, everything is always D modules. When you make the story we're discussing now, if K is not 0, is going to be more like that second one.
I see.
Duality statements, but they all have Hecky-like functors. There never wasn't like functors. You never got a classical picture with O pairs. I don't think. again, I need to say that Davide knows more about it than I do. And he keeps telling me that we should, well, delve into it more than we have.
I mean, it's related maybe to things that Edward said in his lectures earlier today and a week ago about this being analogous to the situation in conformal field theory, where you couple holomorphic and anti-holomorphic blocks.
Yes, that's a good analogy, but I agree.
So like here, for example, you will not have quantum Hitchin system when k is not 0, but you will have some kind of Knizhnik-Zamolodchikov equation, which will be replaced by like in genus 0 Godin equations, which is quantum Hitchin.
Yes, but that has a different, well, at least in the context of conformal field theory, then you're not talking about a fixed C, a fixed Riemann surface. That tells you, okay, no. Well,
that's right, because there will not be a theory for fixed Riemann surface. You will have to move around.
Well,
yes.
Well, it depends on, there are various things you could try to get, but there really is something where k is an integer, and you do study an L2 Hilbert space, but the types of statements you can make about it don't have the same flavor as they do when k is 0. That's because there's no dual description involving O pairs.
And just one more quick question. Do you have any picture for when instead of complex numbers, we have real numbers? So KK operators over real numbers and the modular space over real numbers.
Well,
what should correspond on a dual side? So I have some ideas, but much worse picture than for complex.
Well, as I say, there are different things you might be interested in. So one theory, which we could discuss, is the case where you want to assume that the Riemann surface is defined over R. Is that the situation you're interested in?
Yeah, for example. Well, I mean, even in genus 0, if you have like some parabolic structures, some points on the real locus with parabolic structures.
On the real axis, then I would describe that by saying that the Riemann surface is defined over R.
Yeah.
So, actually,
may I make a comment in this case?
Well, I'd like to ask, I was about to say something. You can hold off for a second. Well, there's definitely something interesting to do, because if C is defined over R, if C is a complex Riemann surface that's really defined over R, that means it has an anti-homomorphic involution. And that means that in this story, you would have had an anti-homomorphic involution without having two copies. And therefore, I believe you can get a theory where Hitchin Hamiltonians will be self-adjoint operators by themselves on functions on a circle. The circle being a real form of the Riemann surface. That kind of stuff.
Yeah, you can do this, but the question is how to describe the eigenvalues. Well, in this case, you describe them by intersecting two Lagrangians, opers and anti-opers. Right. But what would be what would physics tell you? What is the description of the eigenvalues in the real case? I mean, we have some ideas, and in some cases we computed it, but the picture is much less clear than in the complex case.
Well, I did, gosh, I wish Davide was in the line, but I think he isn't. I promised him I wouldn't say anything he didn't know, and that might have discouraged him, but it turns out questions are coming up that he knows better than me. In one of our papers 10 years ago, we studied geometric Langlands with real involutions, which I think will be relevant to this. But I don't want to say more without brushing up on that paper, actually.
Thank you.
I guess we're getting too late, but maybe was there one more question? Or?
I should better say we studied n equals first group Yang-Mills theory with real involutions. The results we did not apply to geometric Langlands. I feel that the spirit of your question would probably motivate doing that. I got a little scrambled in saying that, sorry.
Well, maybe we will discuss after the talk
fine.
at some point over email.
That would be fine. I'll have to look at the paper though, and definitely get David in this discussion.
Mhm. Thank you.
Sure. There was someone waiting to ask a question.
I just had, thank you. I just had I guess, a trivial comment related to this previous discussion. So if the curve is defined over R originally, and you consider it as a complex Riemann surface, it has an anti-holomorphic involution, as you said.
Yes,
And you can also pull back a Higgs bundle by this anti-holomorphic involution, which induces an anti-holomorphic involution on the Higgs moduli space. And the fixed point set of that, I believe, is a Lagrangian subspace. It's the locus of real points on that. So you could consider.
That's the kind of stuff I had in mind.
Yeah. So you can consider home of this Lagrangian with the BCC. So it would give you some kind of Hilbert space, which depends on the arithmetic of the curve. I actually wanted to ask you this. I'm happy somebody else brought it up.
I don't think it would. Arithmetic, I think, is too optimistic.
Well, okay, yeah, because it's only capturing the Galois group of C over R, so just this anti-holomorphic involution. But it's still,
yes,
it's still something.
It makes sense separately for each real component.
Yeah.
But that situation makes perfect sense, and yeah, I think one would be able to say interesting things, but I can't make a promise of that. The ability to say interesting things might depend on the group G.
Right. Yeah. So I will explain what we know about the real case in the talks at the Greenfield seminar, like next week and the week after probably, and then we can see if this agrees with this picture. It would be very exciting if there was a conjecture in general.
It would, if it agrees with that picture, it would agree with things that haven't been done with that picture, this picture. But anyway, yes.
So a much more trivial question. I just want to understand this. So can you describe this magic A coisotropic brane BCC in terms of Higgs bundles?
Well, it's defined for any complex symplectic manifold that you view as a real symplectic manifold.
Yeah, so and if I take your Y to be the moduli space of Higgs bundles and want to describe this locus precisely as a...
Well, there's no locus. This canonical quadratic brane is supported on the whole manifold. So,
yeah, I see.
So you see, I won't tell you anything interesting that depends on Higgs bundle moduli space. It's a general definition for any complex symplectic manifold that you view as a real symplectic manifold.
Right, okay. No, I had that wrong. So its support is the entire variety. It's the entire Higgs moduli space.
Yes.
I see. Thanks.
And importantly, it comes from a construction in 4 dimensions. Well, that's important for all kinds of technical reasons, but as I mentioned, it was originally hard to understand physically what is the dual of diff itself, differential operators itself regarded as a D module, until we understood an improved 4-dimensional picture for that brane. And that let us understand that the dual was the structure sheaf of the variety of our pairs.
I just maybe can I ask one last. So the quantum Hitchin system is a regular local system which has regular singularities on this divisor of not very stable bundle, which is also called wobbly divisor. So it can be described. There are a lot of papers about this divisor, but then the question is, can you calculate the eigenvalues of monodromy of the system around this divisor? Does it physics tell you anything about that?
I suspect that the answer is it doesn't tell you anything that isn't obvious mathematically.
Well, it's not obvious what they are. I mean, you can compute them in some examples, but according to Denis Getsgori, it is not known, and it is not easy to calculate.
Well, as you can see, I don't know anything about it. I would have hoped that there was at least for the generic behavior near that, at a generic point of that divisor, I would have hoped there was a simple local model that you could use. But I would have assumed that mathematicians have already done that if it exists.
Well, it's not completely trivial. I don't know. I mean, yes, you're right. In principle, there should be computable, but it's not so easy.
Okay, great. Well, I guess it's getting a bit late, so maybe it's reasonable to stop at this point. So whoever is left, I think we should thank Edward again for this energetic, long exertion. Thank you so much. Thanks again, and I hope it's okay if I invite you again sometime.
Sure, anytime.
Yeah, thank you. Bye.
Okay.